Today I'm going to try to clarify the different airspeeds pilots need to know and understand. At the end of this video you should have a clear idea of what these 5 airspeeds are, why we need to know about them and their practical implications. Pilots only need to read the 3 speeds in blue off of their instruments: ground speed, indicated airspeed and true airspeed. The other 2 airspeeds are used by engineers to calculate true airspeed under different conditions. Ground speed is the speed we are all familiar with. Speed equals distance over time, usually expressed in nautical miles per hour, called knots. We can use this practically for navigation and estimating time of arrival. If Mr. Gates's Bombardier can average 500 knots and the flight distance from New York to London is 3,015 nautical miles, we can tell him that our flight time will be 6 hours and 2 minutes. To understand indicated airspeed, we need to understand how it is measured using the pitot-static system. The altimeter and vertical speed indicator on the right only needs static pressure. As the static pressure changes, the altimeter and the vertical speed indicator record these changes in static pressure. For the speed indicator, we have a pitot tube pointing head on at the airstream. We measure that pressure. We also have a static port which measures the static pressure. When the aircraft is still, the pitot pressure and the static pressure are the same and the indicated airspeed is 0. The faster we go, the more air molecules ram themselves into the pitot tube, and we call that the ram pressure. We measure the difference between the pitot pressure and the static pressure at different speeds and assign a speed value in knots to that pressure difference. So here we are calibrating our indicated airspeed gauge. We are using international standard atmospheric conditions. That is to say, we're at sea level, there's no wind, the temperature is 15 degrees C, humidity is 0%. Our Tesla has an ultra-accurate speedometer measuring our speed in knots. We are matching our ground speed to exactly equal our indicated airspeed under these conditions. What we are really doing is matching our ground speed to the pressure difference reading in our pitot-static system. We call this speed indicated airspeed, but we can think of it as pressure or force speed. Under these conditions, indicated airspeed, ground speed and true airspeed are all the same. We now take our Tesla to 6,000 feet with our calibrated pressure speed device. We now see that when our pressure speed measures 100 knots, our Tesla's ground speed is 113 knots. Because there is no wind, this is also our true airspeed. It turns out that the less dense the air gets, the faster we have to go to generate a pressure speed of 100 knots. The density of air depends mainly on altitude, but also on temperature and very slightly on humidity. So the clever aeronautical engineers, using the incompressible Bernoulli equation, devised a way to calculate true airspeed at any given air density. To work out air density, you need to input altitude and temperature. You then input the indicated airspeed, and true airspeed is calculated. Why on earth did we invent such a weird way of measuring airspeed? Well, it turns out that indicated airspeed or pressure speed is directly related to the forces on the wings for takeoff, stalling, and many other speeds that we need to fly an aircraft. The good news is that all our indicated V-speeds are the same no matter what temperature or altitude we are at. Imagine if our airspeed gauge indicated true airspeed. We would need to have tables for each altitude and temperature to know what our VR speed and all our other V-speeds are. Our VR speed and stall speeds when we use indicated airspeed are always the same. Let's have a look at some practical implications in our twin-engined Beechcraft Baron. The red line on the speed indicator represents VMC, or the minimum speed to make our plane controllable on one engine. The blue line, VYSE, speed is our best climbing speed if one engine fails. So we usually rotate at red line plus 5 knots, which is about 90 knots, and then wait for 101 knots, the blue speed, before we pull back more for a steeper climb. Let's have a look at these implications if we want to take off from different airports. JFK is virtually at sea level, so our VMC is 84 knots and our true airspeed is also 84 knots. Our VYSE is 101 knots and our true airspeed is also 101 knots. At Jeffco in Colorado, the altitude is 5,700 feet. Now when our speed indicator says 84 knots, our true airspeed is 93 knots. The true airspeed at blue line speed is now 112 knots. At El Alto International in Bolivia, at an altitude of over 13,000 feet, our true airspeeds jumped to 108 and 130 knots respectively. True airspeed is important for navigation. It is expressed as TAS or KTAS for knots. It's the speed at which air is moving over our wings. True airspeed will be ground speed minus tailwind or ground speed plus headwind. Calibrated airspeed is indicated airspeed corrected for pressure error measurements. Pressure error measurements are caused by instrument error, position error. It is impossible to put the pitot tube in a position that will be accurate under all conditions. Also, the static pressure should be far field, that is to stay measured away from the aircraft. This also can't be done. In fast climbing aircraft, there is a pressure lag error. Thus, calibrated airspeed is airspeed that is calculated from indicated airspeed. Below 1,000 feet and 200 knots, the difference between IAS and CAS is negligible. Why do we need calibrated airspeed? Engineers need it. It is more accurate than IAS as an intermediate step to calculate true airspeed. Accurate speeds are important for aircraft control and design. By law, IAS gauges cannot differ from calibrated airspeed by more than 3% or 5 knots, whichever is greater. In most situations, it will be less than that. So 1 or 2 knots in our Cessna at 100 knots is acceptable. Equivalent airspeed. By the 1930s, aircraft were flying high and fast. Calibrated airspeed was not accurate at high speeds greater than 200 knots and altitudes greater than 20,000 feet. Because it was useful for predicting aircraft handling, aerodynamic loads and stalling, it was important to find something more accurate. At high speeds and altitudes, air no longer behaves as incompressible, and Bernoulli's compressible equation was to be used. At high altitudes, a lower pressure speed will correspond to true airspeed. This amounted to a density correction. Here is a graph showing these speeds at different altitudes. You can see that with altitude, true airspeed increases with respect to both EAS and CAS at approximately 2% per 1,000 feet of altitude. At high altitude, you can see that the EAS is much lower than the CAS, and this is the speed that engineers need to calculate true airspeed, to determine stall speeds and predict other aerodynamic forces. Here is a summary of what we have been talking about. Calibrated airspeed is indicated airspeed corrected for pressure error correction. Remember, we said this was done due to 1. Instrument error, position error, and lag pressure. Equivalent airspeed is used at higher altitudes and speed to correct for the fact that air now behaves as a compressible gas. True airspeed can then be derived from this equivalent airspeed by correcting for density at that particular altitude. This can all be easily remembered by using the mnemonic iced tea, pretty cool drink. I hope that this has been a clear explanation of airspeeds and their practical applications. Thank you for listening, and goodbye.